mine is the last presentation today, and I'll try to, keep it within 15 minutes so that we have some time for question and answer at the end. So this is work that we have been doing since 2024. Ours is RA5 and working with students and a lot of the researchers here at for Sentry, because we'll try to show you how it kind of fits in with the work that is going on in other research thrusts. So the challenge, we have been talking about that throughout the last two presentations as well. So Sentry obviously has this big umbrella for or the goal for protecting soft targets, but we are focusing specifically on mass shootings. And within that, we are also more closely working on schools. And we have seen that these attacks come in various different ways, different methods, starting from really big casualties such as the one in Las Vegas, the Las Vegas Strip massacre in 2017. Completely different from the school shootings. So each one has its own way of unfolding over time. And the question that we are trying to answer in Sentry, all the research thrusts essentially, is what can we do and how can we help in decision making, and whether that be before the event or during the event in real time. So we tried to kind of separate the response into three different categories. The first one being what we can do before an event like that happens in the way of preparations, in the way of fitting or instrumenting an area with sensors. So those kinds of preparations include if we can do any kind of architectural augmentations. And this is work that is being done heavily in RD4. We are collaborating with them. Maybe change some of the architectural features like the width of the doors, which enable more people to get through in critical locations. Planning and lockdown protocols, training and drills. These have always been very important, and these are also going to be important going forward, even with the newer things that are coming out of this research. In order to implement this, drills and training is going to be crucial. Now, what we are in our project, what we are interested in is the infrastructure setup. So in that category, the research questions specifically for us were, okay, we understand we have to instrument a place, but what is the optimal locations where we can place cameras and other sensors? And that will be dictated by a lot of things, such as the range of the camera, the frames per seconds that we can analyze, the field of view of the camera, and also the graph, the map of the environment, such as which are the more easily accessible places where the shooter is more likely to visit. Other research questions are, if we are to tell the people or inform them or guide them in any way, we have to get that information to those people. And our method for doing that is using dynamic signs. So that will change based on recommendations from the optimization. Now, positions or locations of those dynamic signs is something that needs to be optimized, and we are looking into that as well. Now, during the event, which is real-time decision-making and support, which is what we are very heavily interested in, that the first part of it is identifying the presence of the shooter, and that is being done in the other research thrusts using video analytics. So tracking the shooter, identifying the shooter, and effectively communicating that information, those are all important parts of this response. What we are interested again in our research is how to provide real-time guidance to evacuees. So real-time optimized routing, and also risk-aware dynamic lockdowns. That means if we were to close down some doors and then reopen them, what would be the schedule? What would be the best way to do it? So we are interested in that. In that way, our research is very closely aligned with Mario's, and they're perfectly complementary, because as you will see, what we are doing is finding the end points. Where should we go? And what Mario is doing is going at one level down in resolution and figuring out what's the best path through the space in order to do that. Figure out what the best splines and polynomials are that the people should follow in order to go from point A to point B. So ours is very much an optimization planning based problem. And we are kind of making some assumptions along the way, which I'll try to explain. So let us suppose we have a floor plan for a school. In here, we are looking at two completely different types of floor plans. The one has a vertical cycle through the stairwells. That's the one in the bottom. And the one on the top right is a simpler one, which has kind of like a tree structure. So these also affect the results very much, and we are going to talk about that a little bit. A brief note about the name, the acronym ASTERS. We have adopted that to kind of talk about the suite of algorithms that we have been developing. It stands for active shooter tracking and evacuation routing for survival. So it makes a few assumptions. It needs to know what the shooter is going to do. And obviously, we do not know that. We can guess, we can use data to kind of estimate. But our plan so far has been to make no guesses at all. We are just going to say that we do not know what the shooter's intents are. So we are just going to model it as a random walk. So it can go in any direction at any point of time. And the other things that we have been thinking about and taking into consideration are the capacities of the different doors and hallways, which play a crucial role in figuring out how to strategically stage the evacuation so that people do not get stuck at the exit points. So if we move on to, like an actual workflow of what we can do, let's suppose we start with this framework, right? So, let's suppose I'm the principal of a school and I have the building layout in front of me. Now, how do I figure out where to place the cameras? That's the first question, considering that we are using cameras mainly for detection. And this can be other sensors as well, depending on context, and where to place the dynamic signs. So we convert this floor into a graph, and then based on some very interesting new measures from graph theoretic measures that came out of the research, we can figure out where are the best locations for placing the cameras based on the graph structure itself and also the type of camera and the coverage of the cameras. So for the sake of argument, let's say we have placed the cameras in these locations, which are the red triangles. Now, what is going to happen is that, let's suppose the shooter is where that pink cross and the pink square is. That is the last known location of the shooter as found by the camera on the right. Now, it is perfectly, it might very well happen that we will lose sight of the shooter, and we are not going to be able to track him constantly over time. So what our model is going to assume is that the shooter can move from its last known location to any of these small orange dots, and the size of the orange dots kind of estimates the probability of the shooter being in that particular location. So the idea is that whatever the shooter decides to do on that particular time, that will be within the considerations that we have already placed, that that's not outside what we had planned for. Now, based on that, we solved an optimization problem using different kinds of strategies for how the people on which are the blue dots should react. Now, the next thing that will happen is the shooter eventually will come in view of another camera, and we will get an update. We will know that, okay, we have localized the shooter's location at this point of time, and the whole process will continue again. So, it's periodic updates based on how densely we can instrument it. We are going to get those updates more and more frequently. But this kind of is a more generic framework where even if we do not get updates, we still have a strategy and a plan in place, and we can push those plans out to the people. Now, I'm going to show you a few results that we have obtained. The graph on the bottom right, that is a graph of the number of casualties against the number of cameras in the particular school that you see on the top right. So this is a fairly simple layout. So 3 cameras are enough, and you will see that the graph kind of flattens out after 3. So adding more cameras does not help. And the locations of the cameras are obviously the most important thing, and that comes out of our algorithm as well. The graph on the left, we have used a, a large number of simulations to kind of vary all the parameters that are relevant and we could think of. So this graph is a little bit difficult to decode, so I'm going to just explain that in a second. So on the bottom left, on the left axis is the seconds spent in the line of sight. That's the vertical axis. And the x-axis is the number of casualties. So obviously the best place to be is at the very bottom left corner, where 0 seconds are spent in line of sight of the shooter and 0 casualties. So the black dots are the experimental results, the simulations that used our Astor's algorithm. And the blue and green and the pink are the dots that came from the same simulations, apples to apples comparisons, where we used a naturalistic behavior where the people essentially just hid until the shooter was nearby and then ran for the exit that was away from the shooter. So this is kind of common sense behavior. And, we are still assuming complete information, perfect information about where the shooter is. And we are just going to run based on that. So we are seeing that the Astor's algorithm performed much better than the naturalistic behavior. So this was very gratifying. There's at least a chance that we can really help if we can provide the right information to the people at the right time. This one, I'm not going to talk too much about this, but essentially this improves the previous simulation by taking into consideration the capacity of the doors and corridors. So if you look at the 3 plots on the bottom left, these show the crowding over time when different kinds of algorithms are used for directing the people out. Without considerations of capacity, if we use the naive way of channeling and routing people, we have these large spikes, which means that there was a large congregation of people, all of them trying to get out at the same time, leading to a very dangerous situation where if the shooter happens to go that way, they will have an easy target for people just waiting and cannot escape. But if we use the right algorithm, using the capacity constrained routing, we can tamp down that spike, and that way we can make sure that staged evacuation lets people out, keeping the time spent in those crowded situations to a minimum. I'm going to skip this. These are some of the newer models that we are trying. Essentially the same approach, same results in the sense that and they have different advantages in terms of complexity and the time required for real-time operation. But essentially, a lot of these algorithms work pretty well. And the gratifying thing is that each has its own advantages and disadvantages and interesting traits, but all of them perform better than what we have now. So there's a huge chance of improving the condition and the amount of information that we can give to people. The last thing I'm going to talk about is this dynamic lockdown, and I don't know if the video will play. Yeah. So this is a video from Nashville, and you can see that in this particular area, the shooter is observed for long periods of time. And what if we could just close these doors and lock them while the shooter was in here? Definitely, it would have resulted in a completely different outcome. And the shooter comes in multiple times. So we tried kind of formalizing that concept and came up with this idea of these lockable doors. And even if, obviously the best thing is to stop the shooter from getting in at all. But if not, if these doors, which you see over here in black, can be locked at the right time, we can restrict the shooter to different parts of the building. Now, here is an interesting question, because if we do that, then obviously in this particular toy situation, we can make a lot of the areas which were kind of unsafe before completely safe, because the shooter cannot breach the door and access those places. But some of the area where the shooter has more access will become more risky. So what we are doing is kind of creating a risk-aware optimized algorithm for locking and unlocking doors, which can let the evacuees escape but keep the shooter contained. So that's the last thing I'm going to show today in terms of results. We are also working on this agentic simulation, agent-based simulation using Unreal Engine, similar to Unity. We have been working on that, and it has a slightly different purpose because we need to make sure that we can control each NPC and move them. This is very exciting for us. We are hoping that the entire pipeline will let us test these algorithms very effectively. So I'm going to stop here. I think I'm about time. So yeah.
Yeah,
and
thanks, Subi.
Hand it over. Yeah.
I appreciate it. So we have time for a few short questions, perhaps from somebody other than Michael.
This is Eddie. Thanks a lot for the presentation. I'm Eddie Washington here. Oh, I see a hand up. I didn't do my hand, so I'll defer.
No, we prefer voice, but Will, you
Okay.
can also chime in.
Just that last point around locking and not locking. So we talked about our systems now where we can remote lock, and the question is, are we locking the students in or locking them out of a particular safe scenario? So when you use a phrase that talked about risk, some kind of a risk aware way to study that.
Can you just repeat the last part of that question?
You said that you were looking at how to manage the risks of the decision to either lock or not lock in that spirit. But like what the value add in certain situations may not be in another, but having that capability to lock the shooter in, so to speak, versus allow people versus locking the students in as well.
Yes.
To them.
Yes.
Yeah.
Yeah. So, like the example that I was showing, that's a trivial situation, right? Everyone will agree that, oh, there is no one there. If you lock all the doors around, you just capture the shooter and no one is harmed.
Right.
But the question is when, you have to play this zero-sum game where a lot of people get the benefit and some people have a higher risk. So instead of looking at risk in absolute terms, we are kind of looking at the increment in risk. So it kind of uses that metric. So, if the increment is small because it is mirrored over a lot of people and the layout is such that it does not really affect it that much. But the benefit is that, the rest of the building is completely secure. Then we can do that. And this is not a decision that, us engineers should take and can take, but it is a tool that puts numbers on risk, and that cause and effect can be at least quantified so that someone who is more suited than us can make the decision.
Yeah, that's very helpful though. It's a good talking point for us who are in that decision making, that matrix and planning. Thank you.
Thank you for saying that. Thanks.
Will, you have a comment?
Yeah, I do. My quick question is just in a nutshell, what is the benefit or rationale behind doing multiple different modeling types of crowds? Like, what is the benefit of having both an agent-based modeling and a predator swarm guided modeling effort?
I'll do a small answer and then I'll ask Mario maybe to pick that up. So I think it's a time scale and resolution problem. So like for us, we are doing the agent-based planning based on different kinds of machine learning algorithms. And that essentially tells people that you have to go from this point to that point. And but when we are doing that, we are kind of at least at this point, we are making some very gross assumptions about the behavior of the people. We cannot tell that exactly how they're going to behave in an uncertain situation like that, whether they're going to respond in a way that we anticipate, and exactly what path they're going to take. So there is a lot of importance in being able to guide the people in a particular path. So Mario, can you maybe, from that perspective, pick that up?
I mean, that's a really good question. And at some point, it boils down to the methods that you want to use. So the methods that we need to use for doing trajectory planning and certifying that your trajectory is safe, you need to be able to analytically project the outcomes of a decision. In other words, you need math models that tells you, if I do this, how are those things going to propagate in the future? In principle, you can do this using agent-based models, but computational complexity kills you because you'll have to do many, many different samples. You have many, many, many particles, and you never know that what you're getting there is representative or not. If you have a validated differential equation, that's a validated model that tells you what the outcome is going to be. So what we hope is we use the agent-based models to actually encapsulate that information in the analytical mathematical model. You can think this as massive complexity representation reduction. Instead of having many, many, many different agents, you encapsulate this in just a few equations that allow you to, with high certainty, predict the future, instead of having to deal with a very large number of particles.
In some sense, Will, I think that you can think of statistical mechanics versus, plotting each individual particle trajectory. Statistical mechanics essentially gives you an aggregate behavior, whereas if you were plotting each individual particle, you might not easily see that aggregate behavior.
Okay, that makes sense. I appreciate y'all breaking it down for me.